Good morning friends. So in the yesterday's lecture we have seen what is a one form. What is a one form is it is a real valued function defined on a TP of E3. What is TP of E3? It is nothing but tangent space which have P as a point of application. That means all the tangent vector which have P as a point of application and different vector path is called a tangent space. So this one form will work as a machine which convert all the tangent vectors or a vector into a real valued function. In the last lecture we have seen two theorem that any one form can be written as summation over I fi dxi, or in another way it can be written as any one form df can be written as summation over I dou fi dou xi into dxi. And we have seen one example. With the help of example itself we have proved that if we are having any one form phi and applied on a vector field b, on the condition any vector field is written in the linear combination of natural frame field. So in this case if you have phi of p, it will be any real valued function. Okay, so let us go for the next one. That is a statement of this theorem is if we are provided with phi is equal to summation over I fi dxi, then it is given that exterior derivative is given by d phi is equal to summation over I dfi into dfi wedge product with dxi. Okay, this is given to us. Now what is our aim to prove? We want to prove that exterior derivative of phi, that if you are want to perform the exterior derivative two times, that is d2 phi should be equal to 0. What is given to us? Phi is equal to fi dxi, and then we are provided that exterior derivative d phi is given in this form, and the next we want to prove that d2 phi is equals to 0. That is, if you have a exterior derivative two times, it should be equal to 0. Why it should be equal to 0? Because if you come to know this, we are having dx wedge product with dx should be equal to 0, or in general we can say dxi wedge product with dxj is 0 if I is equals to j. So let us go for the first one. We will evaluate this expression d phi so that we can perform the exterior derivative d2 phi for this expression itself. Okay. So let us evaluate this. For this, f is a real valued function. So what will be df1? By the theorem which we have seen in the last lecture, it should be equal to summation over I dou f by dou xi into dxi. So instead of having f, we have a function f1. So it will be dou f1 by dou x1 dx1 plus dou f1 by dou x2 dx2 plus dou f1 by dou x3 dx3. Wedge product with dx1, this term as it is. Secondly, what is expression for df2? Again it is dou f2 by dou x1 dx1, dou f2 by dou x2 dx2, dou f2 by dou x3 dx3. Wedge product with this term dx2 as it is. Let us evaluate the third term, that is derivative of total derivative of f3, that is dou f3 by dou x1 dx1 plus dou f3 by dou x2 dx2 plus dou f3 by dou x3 dx3 wedge product with dx3. Okay, so whatever the expression we have been provided, we have written it in the more evaluated form. We have written the expression for df1, df2 and df3. This you have studied already in the BSc, that how to write down the total derivative of any function with three variables, say x, y, z, or instead of x, y, z we can have x1, x2 and x3. So whatever we are discussing in the differential geometry is concerned with only E3 space, Euclidean space, or R3 space. Now, if you see this expression, total 3 plus 3 plus 3, we have to evaluate 9 terms. But we know dx1 wedge product with dx1 is 0. Similarly, dx2 wedge product with dx2 is 0. dx3 wedge product with dx3 should be also 0. So out of all those 9 terms, we will remain with only 6 terms. Why this is so? Because we know that exterior product or a wedge product of a one form with itself should be equal to 0. So in the first term, we will have the first term is 0. In the second term, we will remain with dou f1 by dou x2 dx2 wedge product with dx1. And then we have the term dou f1 by dou x3 dx3 wedge product with dx1. In the second term, we will have dou f2 by dou x1 dx1 wedge product with this dx2. But the second term of this expression should be 0. Why? This is dx2 wedge product with dx2 is 0. Next, dou f2 by dou x3 dx3 wedge product with dx2, it is equal to this term as it is we have written in the here. Next step. Now let us write down for the third term. In the third term, we will have the first and second, and the third one will be 0. So after evaluating this, we out of 9 terms, we will remain with only 6 terms. Now we want to write down this 6 term in a very compact form. For that, we must know that dx psi wedge product with dxj. That is, if we have phi wedge product with psi is equal to psi wedge product with phi, but with the negative sign. That is, if we want to work for any vectors. So for this, suppose we have any vector a bar and b bar. So what is the resultant of this vector if you want to evaluate the cross product? The resultant of the cross product is always in the upward direction, and this vector whatever we are getting a cross b, which will be perpendicular to both the vectors a and b. So in the very similar way here also we can see if we are having a wedge product of any two one form phi wedge psi, it is equals to minus of psi wedge phi, just like a cross b is equal to minus of b cross a. That is, it does not obey the abelian property, and hence we can say these two are equal, but with the sign is changing, that is with opposite sign. If we want to write down this, that is dx 2 wedge product with dx1, so this will be with the negative sign, and here it is dx1 wedge dx2. So hence we can take dx1 wedge dx2 common outside, and in the bracket we remains with this term. Secondly, we have x3 x1, here also we have x3 x1. So now we can write for x3 x1, so this term as it is, and if you want to change this order, if you want to change the order of a wedge product, we must introduce with the negative sign. So here f3 with respect to x1 will be with a negative sign, and what we remains outside in the bracket is dou x3 wedge product with dx1. So what we remains in the last term is dx3 wedge product with dx2. So what we have the terms here, if we see the second term is f1 with respect to x3, sorry, f3 with respect to x2, and here f2 with respect to x3. And hence finally we get this expression. Okay, so now we have got the expression for d5. Now let us write down the expression for d25, that we want to prove d25 should be equal to 0. But if you see this expression very clearly at this time, if you are evaluating the again the exterior derivative, it should be equal to 0, because if you see here we have a wedge product of dx1 dx2, here wedge product of x dx1 dx3 and wedge product of dx2 and dx3. Now if you want to evaluate once again an exterior derivative, you have to perform this expression once again. That is, whatever the term we have here, we have to take a exterior derivative of this term. That means again you have to evaluate this summation. So for this term itself only, we have to evaluate the whole summation. For the second term again we have to evaluate this whole summation, and for the third term also. Okay. For if you are evaluating this function, whatever we are getting, it will be one real valued function. Why this will be a real valued function? Because f1 itself is a real valued function, and you are evaluating the partial derivative of this. So whatever the expression we are getting for this bracket should be again one real valued function. For that only, if you are evaluating the exterior derivative, again you have to go with this df1. Instead of f1 now, we have this total expression. Whatever the function we are obtaining, we have to perform a d of this expression. D of this total expression. So let us go for the next one, how to evaluate exterior derivative. So d25 will be d of phi, that is we have to perform the derivative of this. So this whatever the expression we have, it will be one real valued function. So if I want to perform the derivative, So again I have to perform the partial derivative with respect to x1. Okay, if I take a partial derivative of this real valued function with respect to x1, and we have to write down here dx1 also. But if you see here in the outside of bracket we have dx1 wedge product with dx2. So obviously the first term should be equal to 0. So instead of having a f1, imagine that instead of having f1 here, we have this whole term. So here we have dx1, here also we have dx1 wedge product with dx2. Hence the first term should be 0. Similarly, we can work for the second term. Again, second term will be equal to 0 because dx2 wedge product with dx2 is 0. So finally we remains with only one term, that is we have to perform a derivative of this function with respect to x3 and wedge product of these two terms with respect to dx3, that is dx1 wedge dx2 wedge dx3, and here we have to perform the partial derivative with respect to x3. Similarly you can work for here we have x3 and x1. So with respect to x3 x1 it will be 0. So first and third term will be 0. We will have only the second term. That is, now imagine f instead of f2 you have this whole real valued function. Why this is real valued function? Again, f1 f3 are real valued function and we are just evaluating the partial derivative. The resultant of all this expression will be again one real valued function. So again, if you want to evaluate the exterior derivative, you have to evaluate this total expression summation over I dou fi dou xi into dxi. Similarly, you can work for the third one, and finally for every expression we have only one term because all the other two terms will be 0 due to this wedge product. Here in the first one we will get expression with x1 x2 x3. Here x3 x1 x2 x3 x2 x1. Now we have to change the order of this so that we can get the result. Okay. So here you can have which as x1 x2 are there, so simply we have to perform the partial derivative with respect to x3, and here we have wedge product with x3. For the second term we have x1 x3, so perform the partial derivative with respect to x2 itself. Okay, remaining term we have x2. Next, perform the partial derivative with respect to x1, and then we will remain with this term. Okay, so now just we have to rearrange the term. That is, now if I want to write down this expression as a one term, so we have to perform a change of order. If you want to perform a change of order, there will be introduction of one negative sign because a cross b is equal to minus of b cross a if a and b are any two vector. In the very similar way, if phi and psi are any two one form, if you want to perform phi wedge psi, it is equal to minus of psi wedge phi, or in general you can have dxi wedge dxj is equal to minus of dxj wedge dxi, and hence now if you perform the two times change of order, it will be minus minus is plus. We'll keep the second term as it is, again performing the change of order. So finally we get an expression in which we have outside dx1 wedge dx2 wedge dx3, and inside the bracket we have all these expressions 1 2 3 4 5 6 terms. So but these 6 terms are nothing but the they are going to cancel. Why? Because if you see here f2 with respect to x1 x3, here also f2 with respect to x1 x3 with positive negative sign. So this first term will cancel with the fourth, second term cancel with this fifth term, and third term cancel with the sixth term. So finally we get one bracket which is 0 and wedge product, exterior wedge product. So finally we get t2 phi is equal to 0. Okay, so let us go for the properties of the exterior derivative. For the properties of exterior derivative, we have to prove these three properties. The first one is very easy. We have only f and g are real valued functions. Phi and psi are the one form. Now just we have to prove that dfg is equal to f dg g df. For that we know already how to write down df. One form is summation over I dou f by dou xi into dxi. Instead of writing for one function f, we have to evaluate this df for product of these two function f and g. Now if you have an expression summation over I dou by dou xi of that function, instead of a function f we have f into g into dxi. Now you can evaluate the partial derivative of product of any two function. How to evaluate this? First keep f as it is, then evaluate the partial derivative of g plus g as it is, then evaluate the partial derivative of f, and then v remains with f and g are the independent of summation, we can take outside. So in the bracket whatever we are getting this expression, if you see here, these are nothing but your df. This df is nothing but summation over I dou a by dou xi dxi, and this expression, and here we have instead of f we have g, so we can write this is dg and this is df, and hence we have proved the first property. Now let us go for the second one. We have to prove that exterior derivative phi wedge psi is equal to d phi wedge psi minus phi wedge d psi. For this we will consider the two cases, in which first we will consider phi and psi with the same dx and dx. In the second case we will consider f dx and g dy. Okay. So if you want to evaluate this term, first we will evaluate phi wedge psi. Okay. So we will have phi wedge psi is nothing but fg, a real valued function, we can take outside. So what will be the resultant? Dx wedge dx, that we have written here. Now okay, so what is f phi wedge psi? We have got it is 0. So what will be a derivative of 0 is again 0. If you take any partial derivative, total derivative, exterior derivative, or rather any type of a derivative of any 0 function should be again 0. So we got the expression 1, that is equation 1. Now let us evaluate the second term, d phi wedge psi minus psi wedge d psi. So for this, first we will evaluate d phi and d psi. So simply you can write this as df wedge dx and dg wedge dx. Okay. And this you can have with the help of last theorem. We have proved how to write down the exterior derivative of any one form phi. It is written as df wedge dx, and here it is psi. Psi is equal to g dx, then d psi is equal to dg wedge dx. Okay, now let us evaluate d phi. We will keep as it is df wedge dx. So next, what is a psi? Psi we have kept g dx minus as it is phi. Phi is nothing but f dx wedge product with what is d psi? Dg wedge product with dx. Okay. So finally, if in the first term, if you see, we have the two terms dx wedge dx. Here also we have dx wedge product with dx. So obviously it is satisfying the associative property we have seen in the last lecture. The exterior product or a wedge product satisfy the associative property. Hence we can have the first term is 0 as well as second term is 0. Why this is so? Because if you are having any one form, wedge product of one form with itself should be 0. So from your expression 1 and 2, you can say that in the case 1 we have the result is true. Now let us prove for the second case. What is a case 2, in which we will select phi and psi with the two different terms f dx, and here it is g dy. F is a real valued function, g is a real valued function. Now let us evaluate this. For this, first we have to evaluate the d phi and d psi. For this, first we will write down the expression for df, and then if you evaluate this expression, the first term will be 0 again. Why? Because dx wedge dx is 0. So we remains with only two terms. Similarly for d psi, again evaluating the d psi, we will get only two terms. Now let us evaluate this term. We want to evaluate this term, then we will evaluate this second term, that is phi wedge d psi, d phi wedge d psi. Then we will subtract these two, and then we will find out phi wedge psi, and then we will take the exterior derivative of this term. So let us evaluate firstly d phi wedge psi. D phi is already with you. Just evaluate wedge product with psi. This is a term for d phi, wedge product with g dy. So resultant is an expression. So in the similar way, we have to evaluate phi wedge d psi. That is, phi is nothing but your f dx wedge product with d psi. D psi is here, this whole total expression. Then after evaluating this, you have to perform a subtraction of these two terms, and then we get this equation 3, that is this term d phi wedge psi minus 5h d psi. Okay, now let us evaluate the second one, that is we have to find out exterior derivative of 5h psi. So what are phi and psi? We have already, it is nothing but f dx g dy. So f and g are real valued function, we can take outside. So fg dx wedge dy. Now if you want to perform the exterior derivative of this term, you have to perform dfg wedge product with dx wedge product with dy. So what is this term dfg? With the first property we have proved just now, this is nothing but ftg gdf. Again you have to write down the expression for dg and df. After writing this, you will get that here we have dx wedge dy. So obviously we will have some terms will be 0 because here dx is there, here dx. Again the first and second term 0, we remains with only third term, right? You see here dou g by dou x dx, and the outside of bracket is wedge product with dx and dy. So first term is 0. If you evaluate this bracket, second term is also 0, third term we will remain. Similarly for the second, and then finally we have to just rearrange the term. If you want to change in order, if you want to change in order two times, with the negative will be positive, and then from expression 3 and 4 you can have, in the second case also we will get the result. That is, what is the second property? d5h psi, that is exterior derivative of 5h psi is equal to d5h psi minus 5h t psi. And for the third property, if I want to prove, I will give you this and homework for you. So in the next live lecture, you have to give me a resultant of this third property. Okay. This is simply function and this is a one form, and you have to prove this result. And this third property you can apply with the help of a second property that we have proved. If you see in the second property, instead of having a one function and a one form, we have two one form. So that's why you can apply the second property for the third property. Instead of evaluating for two one form, we have one function and another is one form. So you can see the expressions are similar, just with this change of sign. So just if you understand the second property, you can apply for the third one and you can get the result. Okay. So now in the next lecture, we will discuss what is a dot product, that I have told you in the last lecture itself. You should know what is a dot product, cross product, what is a geometric interpretation of a dot and cross product. And after that we will have an inner product, and next we will see the norm also, that you have already studied in the functional analysis. What is a norm, what are the four properties of norm, how the norm is defined, what is a geometric interpretation of norm, and what is a relation between norm and inner product, what is a difference between norm and modulus, what the norm will measure, it will measure the distance from origin, and what is the property of a modulus, that what the modulus is going to measure. And the next one we will see what is dot product of any two vector, how it perform. Next we will see how the inner product is nothing but the generalization of our dot product, because dot product, if you are evaluating, we will have only two vector a and b, but if you want to evaluate the inner product, we have a and b are some expressions we have been provided. So for inner product is nothing but our generalizations of dot product. How you evaluate the dot, but a dot b is equals to mod a mod b cos theta. In this figure itself we can see how the cos, why we are writing cosine itself. In the last live lecture also I have asked you why we are writing cosine for the dot product and why we are writing sine for the cross product, and what are the geometric interpretations of those cross and dot product. After that only you will understand why the inner product will be a generalization of a dot product. Okay. I think already this have been done in this is completed in our functional analysis. Maybe in the Hilbert space you will have this. that how to perform the inner product, or rather in the linear algebra itself you will see you have seen that how the inner product is written. But now we will see this inner product as a generalization of a dot product. Rather, dot product is originated from our simple calculations. That is, suppose if you want to work for what is product of 2 and 3, directly you will say it is 6. But if you want to perform this for on 2D or 3D space, right? So in the next lecture we will see what is a dot product. Before that you must know, you must come with what is a geometric interpretation of dot and cross product, and why we are writing the sine and cosine for those number, why we haven't used any other trigonometric expression. Rather we can use a tan, cotan, tangent, cotan, even cosec. We can use another some another expressions, uh, and we can use some. Suppose if you want to write down for a dot b, I can have mod a mod b sine theta, but we are writing cosine of this. You must know for this, and I want to tell you that I have shared all the notes of Shivaji University. 7 notes I have shared you in the Google Classroom. You can download it from there. And in the next one, I will show you this. From the Google Classroom itself, you can download this recommended book. That is Differential Geometry by O'Neill B. And next, I have shared you the notes of Shivaji University itself. So let me see this. So total, I have shared you 7 PDF in which you can have the total notes of differential geometry. All the solved examples are also there. And if you want to see the exercises, if you want to solve the examples of the exercises, you can go for the recommended book which was written by O'Neill B. And I suggest you to download that O'Neill B book. That will be beneficial for you to understand the differential geometry paper very clearly. Uh, Next, so, okay, let us stop here. We will have the next one, that is what is norm and inner.